Welcome back to Lesson 9 of our journey through the TCP/IP model. We've already passed through an overview and then the application layer, and now we're in the midst of the transport layer. And we just finished a 3-lesson set on the stop and wait protocol at the transport layer. Now we're going to turn to a more effective approach to verifying or validating data from one end to the other. So let's pick up where we left off. If we define the utilization of the sender or the channel as a fraction of the time the sender is actually busy sending bits into the channel, the analysis of this figure 318 shows that the stop and wait protocol has a rather dismal sender utilization. The solution to this particular performance problem is simple. Rather than operate in a stop and wait manner, the sender is allowed to send multiple packets without waiting for acknowledgments. If the sender is allowed to transmit 3 packets before having to wait for acknowledgments, the utilization of the sender is essentially tripled. Since the many in-transit sender to receiver packets can be visualized as filling a pipeline, this technique is known as pipelining. Pipelining has the following consequences for reliable data transfer protocols. First, obviously, we cannot continue to use only a 0 and a 1 for sequence numbers. The range of sequence numbers must be increased since each in-transit packet, not counting retransmissions, must have a unique sequence number, and there may be multiple in-transit unacknowledged packets. The sender and receiver sides of the protocols may have to buffer more than one packet. The sender will have to buffer packets that have been transmitted but not yet acknowledged. Buffering of the correctly received packets may also be needed on the receiver side as each packet is being processed. So both sender and receiver are buffering. The sender is buffering packets that have not been acknowledged, and the receiver is buffering packets that have not been processed. The range of sequence numbers needed and the buffering requirements will depend on which data transfer protocol is being used to respond to lost, corrupted, and overly delayed packets. 2 basic approaches toward pipelined error recovery are go back in, as you see here, go back in, and selective repeat. The most significant difference between the two is when using go back in, the receiver only acknowledges when the entire group has been received and does not acknowledge anything if there's a gap in the sequence. So if the sender is sending 3 packets, it's not going to acknowledge until it has received all 3 packets. Selective repeat acknowledges each packet. With go back in, the timer is set to the last packet in the group, and if a timer expires, the entire group is resent. With selective repeat, only unacknowledged packets are resent, thus the name selective repeat. In a go back in protocol, the sender is allowed to transmit multiple packets without waiting for an acknowledgement, but is constrained to have no more than some maximum allowable number of unacknowledged packets in the pipeline. That would be the N in go back in. When this lesson is over, the authors would like you to play with the GBN applet at the companion website. You see the address down at the bottom of the screen. You can make a note of it now, or you can come back and get it after the lesson is finished. It's interesting, but the course developer was unable to get the kill button to work. Maybe you'll have better luck. Figure 3.19 shows the sender's view of the range of sequence numbers in a go back in protocol. If we define base to be the sequence number of the oldest unacknowledged packet and next sequence number to be the smallest unused sequence number, that is the sequence number of the next packet to be sent, then 4 intervals in the range of sequence numbers can be identified. sequence number in the interval of 0 to base minus 1 correspond to packets that have already been transmitted and acknowledged. The interval base to next sequence number minus 1 corresponds to packets that have been sent but not yet acknowledged. Soon. Sequence numbers in the interval next sequence number to base plus n minus 1 can be used for packets that can be sent immediately should data arrive from the upper layer. As suggested by this figure 3.19, the range of permissible sequence numbers for transmitted but not yet acknowledged packets can be viewed as a window of the size n over the range of sequence numbers, as you can see here. There's your window size n. Figure 3.19 shows the sender's view of the range of sequence numbers in a go-back-n protocol. If we define the base of the sequence number to be the oldest unacknowledged packet, that's this one right here, and the next sequence number to be the smallest unused sequence number, that would be this one right here, that is the sequence number of the next packet to be sent, then 4 intervals in the range of sequence numbers can be identified. Sequence numbers in the interval of 0 to base minus 1 correspond to packets that have already been transmitted and acknowledged. The interval base to next sequence number minus 1 corresponds to packets that have been sent but not yet acknowledged. Sequence numbers in the interval next sequence numbers and base plus n minus 1 that can be used for packets that can be sent immediately should data arrive from the upper layer. As suggested by figure 3.19, the range of permissible sequence numbers for transmitted but not yet acknowledged packets can be viewed of as a window the size n, as you can see here. This is over the complete range of sequence numbers. As we have already learned, the n is the number of packets that can be sent before an acknowledgement must be sent. As the protocol operates, this window slides forward over the sequence number space. For this reason, n is often referred to as the window size, and the go-back-n protocol is referred to as a sliding window. You might be wondering why we would even limit the number of outstanding unacknowledged packets to the value of n in the first place. Why not allow an unlimited number of such packets? We'll soon learn that flow control is one reason to impose a limit on the sender. For the moment, let's just recognize that the receiver has to process a packet when it arrives, and it only has a limited amount of space to hold more packets while it does so. In practice, a packet sequence number is carried in a fixed length field in the packet header. If k is the number of bits in the packet sequence number field, the range of sequence numbers is therefore 0 to 2k minus 1. The sequence number space can be thought of as a ring of size 2k where the last sequence number, 2k minus 1, is immediately followed by sequence number 1. Figures 3.20 and 3.21, as we'll see in a moment, give an extended model description of the sender and receiver size of an acknowledgement-based, negative acknowledgement-free, go-back-n protocol. We refer to this model description as an extended model because we've added variables for base and next sequence number. And we've added operations on these variables and conditional actions involving these variables. You can look these over on this screen to help you understand the process later. Simply go back to the video and pause it. The go-back-n sender must respond to 3 types of events. First, an invocation from above. When RDT send is called from above, the sender first checks to see if the window is full. That is, whether or not there are n outstanding unacknowledged packets. If the window is not full, a packet is created and sent, and variables are appropriately updated. If the window is full, the sender simply returns the data back to the upper layer, an implicit indication that the window is full. The upper layer would have to presumably try again later. In a real implementation, the sender would have likely either buffered and not immediately sent this data, or it would have a synchronization mechanism such as a semaphore or flag that would allow the upper layer to call RDT send only when the window is not full. The second event is the receipt of an acknowledgement. In our go back in protocol, an acknowledgement for a packet with a sequence number N will be taken to be a cumulative acknowledgement. Get that, cumulative acknowledgement, indicating that all the packets with a sequence number up to and including N have been correctly received at the receiver. Remember, we said go back in does not acknowledge every individual packet, but it acknowledges packets in groups. We'll come back to this issue shortly when we examine the receiver side of go back in. And thirdly, there is a timeout event. The protocol's name, go back in, is derived from the sender's behavior in the presence of lost or overly delayed packets. As in the stop and wait protocol, a timer will again be used to recover from lost data or acknowledgement packets. If a timeout occurs, the sender resends all packets that have been previously sent but that have not yet been acknowledged. Our sender in Figure 3.20 uses only a single timer, which can be thought of as a timer for the oldest transmitted but not yet acknowledged packet. If an acknowledgement is received, but there are still additional transmitted but not yet acknowledged packets, the timer will be restarted. If there is no outstanding unacknowledged packets, the timer will be stopped. Here's 3.21. The receiver's actions in go back in are also simple. If a packet with a sequence number N is received correctly and is in order, the receiver sends an acknowledgement for packet N and delivers the data portion of packet N to the upper layer. In all cases, the receiver discards the packet and resends an acknowledgement for the most recently received in order packet. Note that since packets are delivered one at a time to the upper layer, if packet K has been received and delivered, then all packets with a sequence number lower than K have also been delivered. Therefore, the use of cumulative acknowledgments is a natural choice for go back in. In our go back in protocol, the receiver discards out of order packets. Although it may seem silly and wasteful to discard a correctly received packet, there is some justification for doing so. Recall that the receiver must deliver data in order to the upper layer. Suppose now that a packet N is expected, but packet N plus 1 arrives. Thus, the data must be delivered in order. The receiver could buffer or save packet N plus 1, and then deliver this packet to the upper layer after it had later received and delivered packet N. However, if a packet N is lost, both it and packet N plus 1 will eventually be retransmitted as a result of the go back in retransmission rule at the sender. Therefore, the receiver can simply discard N plus 1. The advantage of this approach is the simplicity of receiver buffering. The receiver need only buffer any out-of-order packets. So while the sender must maintain the upper and lower bounds of its window and the position of next sequence number within this window, the only piece of information the receiver need maintain is the sequence number of the next in-order packet. This value is held in the variable expected sequence number shown in this receiver state machine in Figure 3.21. Of course, the disadvantage of throwing away a correctly received packet is that the subsequent retransmission of that packet might be lost or garbled, and then even more retransmissions would be required. I think that's enough for this unit, this lesson. There'll be more lessons in this section, so just take a break, go back and take a look at your notes, look at your additions to your checklist, or not your checklist, but your study guide, And after you've refreshed and ready to come back, come on back. We'll go on to the next lesson.